Thank you for coming and for inviting me. I was writing down this title to try to attract you, because I know that you are interested in forests and deforestation and what's going on river basins. But in my interest is mostly what's the effect of what happens in the river basin on the rivers, and also on the coastal areas, right? I will mostly work on deltas. They are the most, let's say, outstanding features, together with estuaries, in coastal systems. But in the end, the issue deals with the connection between the river basin and the land uses and the climate and the geology and everything happening or being in the river basin, and the connection with the coastal area. And that means that we need to understand the processes involved in this case in hydrology, but especially in sediment transport, right? Because if we want to understand what's the consequence of what we do in the river basin in regards to the coastal area, we need to understand about sediment dynamics, especially in rivers. So we were, in this case, and this was, I will show you later, was a paper published last year in Global and Planetary Change. I wanted to make a new approach, let's say through a worldwide database, in which we could maybe see what's the effect of land uses in general, not only deforestation, or land use changes on coastal areas, on sediment delivery, and then on the landforms like deltas, right? Deltas could be like, let's say, an indicator of what's happening in the river basin. And in this case, the dependent variable was essentially the delta size, nothing but delta size. And trying to connect this variable with processes in the river basin, mostly large scale, from centuries to millennia, not mostly related to the processes happening in the last decades, right? Especially in relation to stronger changes in land use, and especially in all the questions related to damming of rivers, which is mostly trapping sediments, so producing a deficit to the coastal area, whereas before that it was mostly about increasing sediment delivery to the coast because of deforestation and other land use changes, right? So that's like the introduction. So we were building a worldwide database with 86 deltas and river basins, right, to investigate the relative importance of deforestation and other land use changes versus, let's say, natural forcings like climate or geology or size of the river basin and so on. And the relevant question in the end was what's the real influence of man on deltas, on coastal areas, in this case on deltas. It has been a lot of debate, right? Because now it's like in fashion, the Anthropocene. It's not a fashion, it's the reality, right? It's very clear. But at some point, and I'll show you later, some papers appearing in the last years were even saying man-made deltas. So it was like the message was, deltas are made by man, by human activities. Nothing to do with natural processes. Well, I don't believe so, right? So we were trying to quantify which proportion of changes in this case in delta size could be attributed to natural forces, natural drivers versus human drivers, right? And we were hypothesizing in advance that we were suspecting that the role of humans in the long run, of course, not in the shorter last decades, like if we talk about retention by dams and so on, but in the long term, in the last millennia, the role of humans was relatively small compared to natural forces. That was the original hypothesis. And here you have the paper. Well, a short introduction to deltas. This is a very nice picture of the Ebro Delta, both. And you see, this top picture is very nice because you can see all this area, which is underwater nowadays, but has been eroded very recently in the last 100 years, or even less, because of the reduction of sediment delivery to the coast. once the sand, especially sand, stops arriving, because sand, almost no grain of sand is crossing the reservoirs, right? Then the delta starts to retreat, especially the most salient part, which is the mouth. So you have, wherever you have a delta, a river-dominated delta that has this like sharp form, means that the river dominates and there is still sediment arriving to the mouth, especially sand, right? Whereas if the delta is like more rounded, that means that it's being eroded by waves, by the sea, and not compensated with new sediments arriving. That depends, of course, on the parts of the world, but essentially this is true, okay? And in this case, the Ebro River is one of the most, let's say, known cases of sediment reduction, because it's more than 99% of reduction of sediments, like the Nile would be similar to the Nile. The Nile is even worse because there is almost no fresh water arriving to the mouth. Whereas in the Ebro, we still keep about 40% of the water, which is not bad compared to other Iberian rivers, for instance, right? But then we also have the problem of subsidence, delta sinking, which is a natural process, sometimes enhanced by humans. In this case, it's mostly natural, so it's from 1 to 5 millimeters per year, depending on the area of the delta. And then we have, of course, sea level rise, which is accelerating, and nowadays we already are in a rate of 4 to 5 millimeters per year, and it's accelerating. So we add subsidence, so we are in the range between half centimeter, 1 centimeter per year of loss of elevation in comparison to the sea level, and that's something that worsens the situation, because that means that we will need even more sediment to compensate this loss of elevation, and we have less sediment, so almost no sediment. So these systems are really in danger for the next decades and centuries if we don't do anything, right? Even if we do things, if sea level goes up and goes up to few meters, that could be the case, quite likely, then we have big problems, because most of the deltas, and in this case the Ebro Delta, is 50% of the surface is less than 50 centimeters of elevation. So it's really an issue, right? And we have all these processes at different time and space scales that are very relevant. The main river switchings, changes of the river mouth, but big ones, happening almost every 500,000 years. That will depend on the delta on the river. That means creating a new delta lobe, building up, and the old one being eroded. So we must, unless some cases you have deltas in which you have several branches and then one is more enforced, the other one, and then you get some kind of dynamics like this. In this case, it's like a new lobe is growing. There is some partial overlapping with the other one, and the other one is retreating naturally. So we always have these dynamics. It's a very dynamic system, right? Major river floods also involve most of the contribution of new sediment to delta growth, right? In quantitative terms. And these nowadays are essentially suppressed in most of the deltas and most of the rivers. Then, of course, major storms, average river floods, then also are very important in terms of sediment supply. Not so much the other processes at lower time scales, but all of them are very important in terms of conforming the dynamics of the system, right, as a whole. So we, in this case, analyze processes mostly involved in the upper part, right, of the processes. Well, the classical theory of delta formation that you could, for instance, read in this paper from Science of Stanley, but there are other papers, says that modern deltas are usually formed after the stabilization, the last stabilization of sea level, like, you know, started to stabilize like 7,000 years ago, and 5,000, 4,000 years ago was mostly about stable, not totally stable, but maybe 1 millimeter per year of rise, depending on regions of the world, of course. So that means that that was the best conditions for the delta progradation, right? And that means that essentially, it's a thing that for me is a little silly. Holocene deltas are Holocene, of course. because we're dealing with Holocene deltas. Another issue, and I have been also investigating about this issue, what was going at early Holocene or even before the Holocene with deltas? And this is another question, because sea level was much lower, right? We don't know exactly what happened, but we are now dealing with this time scale of, let's say, 5,000 years in which deltas prograded in under stable sea level. Okay? And then this paper from 2013, focusing mostly on Mediterranean deltas, analyzing some data from, was stating that actually these deltas and many other deltas could be like made by men. This is quite a strong statement, right? So we didn't believe that. I live in the Ebro Delta and I know that it's not man-made, right? But it's true that it's one of the dramatic cases from these people defending this hypothesis, is that the Ebro Delta, some people, and that's being published in some scientific papers without any, fundament, that actually even originated under Roman times or even during Muslim times because of the deforestation of the Ebro Basin to build the Spanish army, navy, boats and so on. It's completely silly if you look at the, but it has been repeated in many papers. So it was like a challenge to show that this is wasn't true, and we could offer new data to show that the Ebro Delta, like the Holocene Ebro Delta, like other Holocene deltas, is started in the Holocene, so like 7,000 years ago, right? This is the paper. Was quite amazing for me because not only they were like showing that like these periods of more activity in the river basin, like Roman Empire, produced progradation of the delta, and then periods of less human activity, like the Middle Ages during the Black Pest and so on, the delta was retreating, and then again during the Industrial Revolution, accreting. And they were trying to show this. But they were making the calculations with very simple assumptions, like volumes and relative positions of the delta front of the coast at some periods of in the past. Very simple data and very, let's say, rough approximation, because we don't have actually good chronology of delta building. And again, it's not that some cases you can find a quick retreat on a quick advance of the delta, but it's because we have had this change in the main river branch. So now the new lobe is always growing very quick because it's shallow, it's a shallow area, and the old one is quickly retreating, right? Once this lobe gets a maturity after centuries, because it goes farther into the sea offshore, and the slope is deeper, it needs more material to build up 1 square meter, 1 new square meter. So at some point it's almost like stationary. You cannot almost build any more delta unless you get a new trajectory of the river and get a new lobe. So that is also tricky, because if you don't take this into account, you can misinterpret the chronology of delta lobes. And in my opinion, is what these guys did. They didn't interpret correctly that. But anyway, it looks like there was some matching between periods of Black Pest and delta lobes and so on, and they stated that. Okay, that's fine. We one of the things we did was take cores, some of them deep ones, these two, especially covering this, the whole Holocene down to 8,000 years. It's like 25 meters. This one also like 25 meters. This didn't arrive to the base of the Holocene. It was like 3,000 years, maybe 4,000. And then the other ones which are shorter to look at more recent changes, like human settlement related to rice cultivation and so on, right? But I will refer a little bit about the two Holocene cores. This was part of the PhD of Xavi Benito. One of the things we did was looking at the paleoecology, looking at the sedimentology, chemistry, and especially the foraminifera, which has been classically used to look at this type of environments, also the marine environments. And then by describing the communities of foraminifera, like indicators of habitat, right, of the different types of environments of the delta, we were able to reconstruct the whole sequence of in this case of almost 8,000 years, 7,500, to show that in this case, essentially this is the water depth inferred, which is always less than 1 meter, and that would be like the type of environments that we would find. So it would be like lagoon, inner bay, sandy, but never near shore or offshore. So we know that at least this part, inner part of the delta, there was never an estuary, because the classical interpretation was that in Roman times everything was sea up to Amposta, and that proves quite clearly that this was not the case, right? And at the same time, it was very interesting because for first time we were able to describe these specific communities of foraminifera, combination of species, proportions, and presence, absence, that could attribute to very specific types of habitats, deltaic habitats, like shallow, bays, coastal lagoons, wetlands, and so on. Because in the past, this type of work made mostly by marine geologists was trying to reconstruct these habitats, these shallow coastal habitats, using marine foraminifera, which is completely different because it's mostly offshore foraminifera or near shore, right? So they were using this information to try to reconstruct what we have been showing here that was not this type of environment, right? So that's an interesting contribution of this paper in this case, reconstructing the whole Holocene. We did the same in this other core, which is farther closer to the sea, let's say, and here that we know that there was these changes in the river mouth because of these changes in the main river course. Here it was different because there was much younger age, much more sedimentation, right? And also big changes in the mouth producing big changes in the sedimentation. That means that here we build up a new soil of several meters, and then the river changes, and then everything is eroded, and then a new delta loft is built in another place. So we always find in these more marine sites part of the sequence that is not there, has been lost because it has been eroded. So you find like a discontinuity of time always in some part of the core, right? 1,000 years without anything or whatever, because here the river is changing, but in the inner part of the delta it's not the case. So then it's always accumulating on the top of, right? But essentially this could prove that the Ebro delta was originally the modern delta starting in 7,000 years ago, and also we did a better chronology of these delta lobes that was, for instance, different from the one that used these guys from man-made deltas. So then computations are also different, right? And here in this paper we also were showing, with this case, with the, let's say, the main model of sediment transport, an hydrological model that is being used by these guys from Colorado, the team of Jim Sivitsky. They reconstruct what are, this is a very well calibrated and validated model with field data of what would be the, let's say, the construction of the hydrology and sediment transport in the Ebro River, and they have been applying this model worldwide in the last 4,000 years, right? This was also interesting to show that during this 4,000 years, in which it represents that at the beginning of this period the condition was almost pristine in the basin, the sediment transport to the mouth was already huge, in the order of 40 million tons per year. And our estimate of sediment transport before dams in the 19th century, because we have some data, it was like, I have a paper on that, close to 30 millions, right? According to this model, it was around 40 millions. Nowadays it's 0.1 million because of the dam trapping. But it's to say that, of course, that the change in in climate, let's say in rainfall, because we have changes in rainfall during this 4,000 years period, and also changes in land uses like deforestation has increased the sediment delivery to the mouth. That would be the difference between a scenario in which only climate is affecting sediment delivery to the mouth. This is the number of, it's a normalized sediment supply per year. And this is when we add the component of the land use changes, like deforestation, right? And of course there is a difference, but still the main component is climate. And climate is, let's say, discharge and discharge variation. Because what has capacity to transport sand, that is actually what builds up deltas, is discharge and floods. So unless we change the hydrology, we cannot transport more sediment. We can transport more sediment, especially fine sediment, because fine sediment can be transported with quite low discharge. So our hypothesis is that this increase in sediment delivery to the coast, which is the case, which is true, is essentially, in most of cases, an increase in sediment delivery in fine sediment, not mostly sand or coarser, right? Which is the one that it's useful for delta building, because the fine sediment goes offshore. And of course in the very long run also contributes to delta building, because it goes to what's called the prodelta, which is underwater, right? It's like a belt of silt surrounding the sandy area. But what really makes deltas to progradate above sea level is sand, right? So, but in any case, this is saying clearly that sediment delivery in a Mediterranean basin, even with more forest, is still very high, because the hydrology and the rain and so on can erode naturally, right? The surface of the basin, and it's high, so it's like the most change was like 40% of variation, but not like 8 times more like in some papers they have published without any real data. In some papers they have said that the sediment delivery to the Ebro mouth increased by 8 times, but without any data. So that's a completely different story, right? And that's the paper. I will show you now the results. And that's a short introduction to the issue of what has been called the sediment delivery problem, because there are many steps involved in when one grain of sand is eroded from the upper part of the basin or wherever part of the basin and arrives to the delta, right? So the first one, and I was looking through all the bibliography. It was very interesting, very nice. I learned very much through this review. In some cases, deforestation and land use change don't always increase land erosion. We could discuss later on if you want about this, but not always. In some cases, it's not the case, right? Then, most of the eroded sediments are deposited very close to the place where they are eroded. Sometimes a few hundred meters or kilometers, and it can take thousands of years to this sediment to get the mouth, if any, right? Then, in some cases, there is a time lag is very, very, very large, especially in big river basins. Then the buffer capacity of the river valley is enormous. That means that you can have a doubling of the sediment suspension in the river, and then because of under natural conditions, of course, there is a flood and overflow, and the creation of the river valley itself, it's a buffer of sediment, right? So you can have a doubling of this sediment in the upper part, and then in the mouth you still get the same amount, because most of the sediment has been deposited along the course, right? So the buffer capacity is enormous. Okay, so then, as I told you, most of the increase in sediment is fine sediment, right? So it depends on what you are analyzing. The fine sediment can contribute or not to some of the processes, right? And then an increase in the fine sediment to the river mouth essentially does not contribute to delta growth, and this is also shown in some papers, right? And then we have the issue of dams, but this is very recent. So then if you look at the recent effect, then things change radically, because then you can state that human influence is huge in sediment transport. It's essentially due to in this case, to the retention, not to the increase. And then, even the most important, there is no good estimates of sediment delivery in most of rivers, not to mention of this buffer capacity along the whole trajectory of the sediment. I mean, the margin of error, let's say, of variability of estimation in each one of these steps, it's huge. So if you sum up the errors you can add, it's impossible to, let's say, have a good measurement of what's going on in the river mouth compared to what's being eroded in every part of the basin. You can make models, you can get some field data, but in the end it's almost impossible to be sure about the numbers, right? So it's very complex. This is why we were trying to make a more an indirect approach, that, let's say, well, if it's true that the influence of man is stronger than natural drivers, we will find cases in which proportionally the delta size will be larger than other river basins similar, in which the man influence is lower. For instance, Mediterranean deltas, which are supposed to be 1,000 years of modification, should be proportionally larger than deltas in which this modification of the river basin is more recent. Right? So with this, we did, this is the 86 deltas. We were able to get good data of everything we wanted to look at, including delta size and all the variables from the river basin. 29 of them were from the Mediterranean and Black Sea, so we were making a sub-analysis of this group, which is an N already small, but still maybe possible to do some multivariate analysis, but it's more in the border of what it's convenient. And we're using a GLM approach to look at what was the effect of these variables on delta size, right? So we were taking delta area, which is the dependent variable, and then basin area, mean basin slope, mean river flow, sediment load, tidal range, shelf slope, that means the continental shelf slope, mean rainfall, dam capacity, mean population density, forest cover, grassland and grassland cover, urban cover, croplands, deforestation rate, dryland cover, percent of habitat loss, and mean human footprint. We were selecting 13, 14 of them out of the 17. Because when you also use these models, if you increase the number of variables, at some point it's not convenient. You have to try to keep the number of variables as low as possible. Okay, so this is the result. To the left is for the whole data set, right? In this type of models, SP, which is the selection probability, one is the maximum. That means that this variable is present in all the models, because this GLM what does is all the possible combinations and tries to look which are the best models, right? So one means that is important variable because it's present in all the models. The closer to one, the more important. And beta, it's the slope. That means that the higher the slope, the more sensitive is the independent variable towards the dependent, right? So as you see in gray color, the most important ones would be especially the intercept is just no matter now. Mean river flow is the main one, but even having more influence is the S1, because shelf slope, it's also one, but the slope, in this case negative, it's stronger. So that means the accommodation space. So the deeper the continental shelf, the smaller the delta, right? Because you need more sediment to build up the delta into the sea. Whereas in positive terms is mean river flow. The higher the flow, the more capacity to transport sand. It's very clear, it's very easy, very simple, right? Sediment load still had an effect, but small. So it was not present in all the models, and the slope was small. And then the other variables, which are in this case more like human influence, they had some effect, but they were not present in all the models, and the slope was always very slow, very almost flat, meaning that there is an effect of population density or urban areas or even deforestation, but the slope is almost flat, so the influence is really small, right? And it was also the case for Mediterranean deltas, right? There was some more influence because here, for instance, urban areas is selected in all the models, but interestingly, it's a negative effect. We don't know exactly why, but in this case, deforestation, yes, it has an effect, right? But it's still small compared to, in this case, would be, in this case, the most important ones were basin area, and well, this is a categoric variable. No, sorry, this is basin area and basin slope. Why? Because in Mediterranean basins, it's most important the slope, the energy of, rather than the average flow. It's more like the flashy floods. It's not very well reflected in the mean flow, right? So it's better reflected in basin slope and basin area, right? And the other one is the same, but just splitting non-Mediterranean and world deltas, including Mediterranean and Black Sea deltas, like a categoric variable. But results are similar, so we'll not lose time on that. And that's the observed versus predicted, and the error is always very high, so the model is able to explain very well the dependent variable, in this case delta size. And in yellow color would be the Mediterranean and Black Sea deltas, which tend to be in this part of the graph because they tend to be smaller, like for instance compared to the Asian deltas, right? But it's just by, let's say, chance. Nile delta possibly would be here, but still they are very well fit into the whole data set, right? Meaning that there are some differences, but still they follow the same type of trend, let's say. Maybe it's too heavy to discuss about this. This is more a detail, but we maybe can discuss that after the in the questions, right? In any case, it was interesting to see that the main effect was mostly the climate driver. So that means that if the climate changes in terms of, for instance, of rainfall, and that influences the mean flow of the river or the floods, the amount of floods and the magnitude of floods, then we will have a strong effect on the delta. But unless climate changes or we change the geography of the basin, which is not possible essentially, then this is the main factors, and human influence. I mean, it is not, you can measure it, you can quantify it, but it's still small compared. And again, this is long term. Large river basins. We were including all the spectrum of size, but most of the deltas are, in this case, are big deltas. If we were analyzing small deltas in small river basins with high slope close to the coast, there possibly the human influence would be stronger, right? Because there is more slope, deforestation can alter more, flow. The connection is very quick in time. So that could be different, the result, but here is grouping the whole range of size, and especially, let's say, medium size and large size deltas. So the take-home message would be like, yeah, I mean, the Anthropocene, it's very relevant, and we're changing. I mean, we're changing the river basin. We're changing the river itself, because I didn't talk about, what's also the influence of, for instance, altering the river itself, because if you narrow the river, if you avoid sediment during the floods, or even avoid floods going to the valley, that means that there will be more sediment going to the mouth. But also because we have been altering all the buffer capacity of the river valleys across the whole river basin. So we alter deltas, we have been diverting rivers and creating new delta lobes, and everything is true. But still, in terms of delta size and contribution of sand to the coast, and the issue of man-made deltas, we have to say that natural processes are still dominant by far. right? And that doesn't mean that human processes are very important, especially in terms of retention, especially the effect of dams. In this case, it's dramatic. But in terms of increase, we must say that the increase has been in the past before dams, impacting mostly on fine sediment. And this is not impacting very much on delta size. It's impacting, of course, in other stories, like even estuaries, classical estuaries, tidal dominated estuaries that rather are inland, not progradating into the sea. And there, because of the tidal dynamics and so on, you have more areas in which fine sediment can contribute to. There, maybe, possibly, it's stronger, the effect of this effect, right? And finally, we're like proposing or clarifying more like these terms. Like, one thing is human-made or man-made. In this case, we would say it's totally man-made or essentially totally man-made. I don't think we have any delta that can be named man-made. Then, of course, human-influenced deltas, almost all of them, and some of them very. We could even have cases in which it would look like it's a new man-made delta, and like would be the case the Yellow River, because the Yellow River was, I was there like 2 weeks ago, and it was very interesting to discuss that and to see that, because this delta 1,000 years ago was not so long, like 1,000 years ago was going to south, far south, like 500 kilometers south than now. And then there was a change, human-made change of a river mouth going to the Bohai Sea, which is 500 kilometers north, right? And of course there, because this new branch was totally away from the old one, this delta was like a new delta. It was a new delta, actually a new delta lobe, not a new delta, but it was totally new, in a different new place. So this is why we could call a man-made delta, but it still was a delta lobe, because the delta was there was a yellow delta, but it was in another part, right? And then I saw that actually this older part of the yellow delta was still both occurring naturally many thousand years ago. So still it's part of the natural dynamics of change of the mouth and the new delta lobes, but in this case the last one was created by man. But in this case you could say a human-made delta lobe, but still a human-influenced delta, right? Or a human-engineered delta, but would be, in this case I would refer more to the case in which the interventions that the man is doing are in the delta itself, like we are constructing levees to avoid floods, we are changing the river mouth, but within the delta. And this is the case in most of the deltas. And that would be, in my opinion, a human-engineered delta, right? So I think this is important to, in the end, to clarify what's going on and try to quantify which is the role of each, let's say, driver. And I think this is all. Thank you.
Thanks very much, Carlos. So my question is on your model, on this, the paper you presented. Of course, the variables related to human influence are mostly related to current, the current situation. And human variables changes quite rapidly compared to the area of the basin, obviously, or climate, which changes much more slowly, and also, of course, the size of the deltas change more slowly, I suppose, relative to human activity. So to what extent do you think that this could influence your results? In other words, even forgetting about dams, if you looked at the rate of sediment transport, would you still expect similar results, or then the influence of human variables would be more important? Or the opposite, if you had more information about human activities that really span, which I would estimate of the past 2,000 years, or would you expect then that these variables would have a stronger influence on the current size of the delta?
I think, yeah, I know what you mean. You mean having more data about land use changes a long time, not like the integration, but yeah, I think we would see more changes, but still, unless the river flow changes, it still would be mostly related to fine sediment, not to sand, because sand, can only be transported with a certain amount of energy, and once it's saturated, it's a non-cohesive transport, whereas the fine sediment is a cohesive transport. The behavior is totally different. But yeah, possibly we would see more like variations, and it's still what this model of the 4,000 years is trying to reproduce. with all the also information about, in this case, in this model, we incorporated the changes of land use every certain number of years, because it's the database of Kaplan, this guy that, right?
Can you extend a bit on which conditions sand is transporting?
Yes, that's very interesting. So let's say that a river flow or a canal, whatever has some capacity of maximum capacity of transport of sand, because it's like saturated condition. Once you get the maximum amount, sand cannot be transported anymore, right? You get sedimentation, extra sedimentation. That means in a natural situation that the river would accrete, and there would be more frequent the overflow, and then more sand would be deposited in the river valley. And that's why the river valleys have been created, which is also interesting, because many times when I talk about deltas, well, you know, deltas, well, come on. I mean, the same can be applied to the whole river valley. I mean, we have nice river valleys, which we use for urban agriculture and whatever, thanks to the overflow of the river and the floods. If we are stopping this process.
But it's just that the sand is going to the mouth.
Yeah, but then the excess of sand is mostly evacuated to the river valley. And there is a very huge capacity of buffer, in my opinion, from the river margins, which is mostly sandy material. Well, you know. Why? Because just a small variation in the capacity of erosion of the river flow, the amount of material that is available in the margins of the river is just amazing. I mean, you can build a whole delta and 100 deltas only by taking 10 centimeters of the river margin along the whole river. So you have there already enough sediment by far to construct a new delta. So the capacity of buffer, it's just amazing. And the sediment is essentially coming, I mean, it's arriving to the river system by anywhere. But the stock being in the river valley and in the river margins, it's a buffer capacity which is impressive. And sometimes we don't think about this.
Yeah, then you just need a flow powerful enough to remove everything.
Exactly, and transport.
Every time that sand approaches to the mouth.
Unless it's evacuated to the river valley.
But in this sense, I was thinking, for example, with GIS images, for example, you can study the river basin and the slopes along the river, and then you may be able to make some calculations of the storage capacity of sand in these areas.
Yes.
And then you can evaluate this compared to the sand available for the delta, or make some comparisons.
Yes, I remember one figure. I was quite impressed about some figures. Like, I think is that all the erosion coming from agriculture, or even all the erosion, can be stored in just 2% of the surface along the river valley or along the river. So it's another impressive figure is that 70% of the world erosion, it's happening higher than 3,200 meters of elevation, where essentially there are no trees. So where deforestation doesn't matter. And this is 70% of the natural erosion. So many times in farming areas, which are quite plain areas, there of course there is some movement of sediment, but real erosion are arriving to the I mean, most of the story is happening in the upper part of the basin.
So would you expect differences in the behavior of the deltas over time in areas where the mountainous chains are very young and high elevation, some more energy?
Yes.
Compared to older mountains which have been eroded over?
Yes, the slope is relevant because it's the amount of energy in the end, either by. Sorry?
You have it in the model, no?
Yes, the slope in the case of Mediterranean deltas, the slope was more important than flow actually. It was a slope and total size of the basin.
So is that because the Alps are relatively young mountain chain? Would you find the same like in Himalaya, as opposed to, I don't know, older, like in the UK, very old mountains, low hills, therefore less energy, therefore...
Exactly, it's two things. One is the elevation of the mountain, let's say of the upper, and the other one is the length of the, because you can have the Himalaya, in which you have a lot of energy in the first part, but then you have a very huge plain. The cases in which sediment delivery it's faster and stronger, it's young or not so young rivers, coastal rivers, small rivers with mountains close to the coast. In this case, the effects of human alteration, they're much stronger. Alpevia, yeah.
So you said that Tortosa was a coastal town in Roman times. But do you know what was the shape and size of the delta in Roman times?
That's a good question. No, we don't know exactly. Possibly it was similar to the size of nowadays. But we don't know exactly. I had to do a talk last year in Amposta. They asked me to talk about the delta in Iberian times, before Romans. And it was very interesting because I was investigating a little bit, and in my opinion, the delta size didn't change very much once you get, let's say, because let's say if you start with a new delta building like the Holocene, at the beginning it's faster, the progradation, and quicker and easier. Then once you get more like into the offshore, it takes much longer to build new deltas. So you get a kind of equilibrium. And almost, I mean, there is never a loss of surface. Even now, there is not a loss of surface. It's a redistribution, because most of these sandy deltas are a closed system in terms of sand. So the sand now being eroded in the mouth is deposited in these spits. So the total delta size is not decreasing. It's not increasing anymore, but it's not decreasing. And then there is another theory, very interesting, of a Japanese guy and American guys, the author retreat theory of deltas, in which they state essentially that once they get some equilibrium, surface and slope with the conditions, marine conditions and the basin conditions, it's like about, reworking and changes, but essentially the system cannot build more surface. I didn't mention that because this is like, in the end, it's even more complicated, right? But yeah, it's and it's interesting to see why, in some cases, these guys were stating that Amposta Tortosa was a marine port, and it was essentially because some ships arrived from the sea. I mean, Tortosa is still a marine port nowadays, and New Orleans also. New Orleans is 100 kilometers from the mouth of the Mississippi, and it's a marine port because boats go upstream and arrive there, but it's not because there was no delta. Or even some cases in which they found remains of a boat in the middle of the river valley. Of course, because the river is changing, and 1,000 years ago the river was 1 kilometer farther than the present course. But doesn't mean that if you find the boat there means that there was an estuary, because it was, so silly things like this that they were not correctly interpreted.
Okay, maybe my question is a little bit naive, but I was wondering, concerning your interest in knowing whether the delta was man-made or was just natural, I was wondering whether in this course that you analyze, whether you can use, for example, ashes or pollen as proxies of pulling the type of vegetation with sediments, or whether there was those big fires or not, or this is something that it's not possible to...
You mean in relation to what happened in the basin?
Yeah.
Some record of things happening in the basin being deposited? Yes.
Yeah.
That would be, of course.
What information does it bring to you?
It could be impressive, but you need a lot of time, people, and money. But I mean, yes, there are this, for instance, Bianchi, it's this guy in Gainesville in Florida, is getting an amazing amount of information from sediments. We're looking at the organic matter and fires and whatever. Yeah, it could be quite impressive, the amount of it. But we don't have, essentially we have here sedimentology and foraminifera and things like this.
Linking with this question, I think in some cases the use of historical information about land use in the basin could be another potential source of
we're supposed to have used the best available data for that. In this paper with Kaplan, because Kaplan is the guy worldwide having the best information about land use changes. And he participated in the paper and he gave us the information about the Ebro Delta, the Ebro Basin.
Historical land use. Well, I don't know which the best source, but in some cases the information is very fragmentary and very qualitative in many cases.
No, this
using Middle Ages sources or
these guys have reconstructed maps.
Yeah.
Of course, using some modeling also.
Yeah.
But
from
very no, from the last millennia.
Okay.
And you get these maps every, I don't know, 100 years or whatever. I don't know the level of correctness, but they're supposed to.
It's the best. It's not a very robot.
Well, I think it's essentially correct.
Yeah.
But of course, it can be improved.
But as far as I understand, the information you need is the hydrology. Because you need these huge flows, bring you the sand, and whatever is in the basin, of course, matters, but what you need to know is the hydrology.
Yes. In the model of the Ebro River, not the delta, the river, there is a hydrological model there, but it's reconstructing the average flow. I agree that if we possibly we could find models reconstructing also the maximum floods, which is very relevant for.
Is the more relevant?
Well, I think the average it's okay because it's reflecting more energy and possibly reflecting more floods. But if we had in the analysis the amount of floods and the magnitude of floods, I mean the evolution a long time, possibly the model would perform better. Right? But we don't have this. I think we could obtain that for some models, not from field information.
But at least historically you only have.
Historically, we have records of floods of the Ebro, for instance, in the mouth. Yes, we have at least a quite good record of the last 300 years. But when you go down to 4,000 years or whatever, you could have it, but you would need a lot of coring and a lot of datation of C14 and so on, which is quite expensive, but you could reconstruct that.
And would this be more relevant than the changes in the forests of the basin?
I think so, yes. Changes in rainfall and climate are the most relevant factors, actually.
So, any other question? No?
I have just a short and related question. Do you know when this picture, this image was taken? I mean, which time of the day?
Of the year?
No, not the year, the day.
The day?
The day, yeah.
Wow. No, I don't know.
I'm looking at it, it's very disturbing because it looks like, probably because of the view of the satellite, the view angle of the satellite, it looks like the shadows of the clouds are pointing to the south. It's a bit weird. So probably it's taken in the morning, in the early morning, so the shadow is going to the west. Well, doesn't matter.
No, I didn't realize about that there, but you are right, yes.
So here we learn both parts. We learn from you and you learn something from
Yes, sure. Yes.
Thank you very much for coming.
Thank you.